So I'm going to give you a few general tips in this video about sample preparation. And let's start with what's the point of sample prep? Well, the big one is to clean up your sample. If it's messy like blood or urine or chocolate or something like that, there's too much stuff in there. You really need to focus down onto your specific sample. So the first thing you're trying to do is pull your stuff out, leave all the rest of the garbage in there. A secondary purpose is to get your sample into a format so that it's ready for the analysis that you are going to do. And I got a bit of a cheat sheet for you here that you can see, you've already seen. If you want to do FTIR, you want your sample to be a solid, or a neat liquid. If you want to do TLC, you want it to be dissolved in solvent. And here's the other techniques that you'll most commonly encounter and the ones that we're going to be looking at this semester. So one of the first steps in extraction or in sample preparation is knowing your sample. And the Swig drug monographs or Clark's are really the best way to do that for us. So here I'm choosing psilocin, and I'm going to go down and look at what's the solubility of psilocin in some common useful solvents. And if I want to do any kind of liquid extraction, I need to know this. So you can see that it's pretty soluble in acetone, chloroform, ether, hexane, methanol, and it's slightly soluble in water. So we can use this information to plan out the extraction. If your sample's a solid like leaves as shown here, then you can try just adding a solvent that your sample likes, typically in a mortar and pestle, and then grinding your stuff up with that solvent and then pulling that solvent away. Now a really important point here and throughout the entire extraction is if you are trying to pull your sample into a solvent, you want no solids. You have to be very, very careful to have no solids. If you have a little bit of solid sitting in the bottom, it's going to junk up your whole sample. So you need to very, very carefully decant whenever you're doing this, or a much better idea is to filter it and or centrifuge it. If you want to be careful, do both, and I would do both, especially when you're starting off. Now, if you're dealing with a solution, or if you're dealing with a solution that you just extracted a solid with, and you want to try and clean it up some more, then you can do liquid-liquid extraction. So you can use two different solvents to try and push the sample from one into the other. A hugely important point here that students often miss is miscibility. All right, if you want to do a liquid-liquid extraction, if you want to have two layers and push the solvent back and forth, push the sample back and forth, that is, you have to have two layers. So you cannot look up, oh, my sample likes ethanol. So you know what I'll do? I'll take my sample that's in water and I will extract it with ethanol. Well, the problem is, if you look at this chart, water and ethanol are miscible. They just mix, they form one layer. You can't separate them out and form two layers. You can't do an extraction with water and methanol or water and acetone. So in the previous slot, in the previous part of the movie, we saw that psilocin likes acetone and methanol and ethanol, but you can't use these to do the extraction. If you look at the miscibility table, you'll see that chloroform is immiscible with water, so you can do that extraction. And you'll see that ethyl acetate is immiscible with water, so you can make two layers using that. But you have to make two layers. And you can see that water makes two layers with lots of things. Ethanol doesn't make two layers with anything. Methanol really only makes two layers with hexane of the commonly used solvents for extractions. There's a few others. But if you're trying to use different solvents that you're unfamiliar with, use a table like this to make sure that you are using two immiscible solvents if you want to form two layers and do a liquid-liquid extraction. So here we have a piece of chocolate that's been ground up in a mortar and pestle with acetic acid. Now, acetic acid you can think of as water. Anything, we call it an aqueous layer. Anything like sodium hydroxide, acetic acid, buffer, if it's something dissolved in water, you can think of it as water when you look at that miscibility table, and we will call it the aqueous layer. So if it's water-based, water with something dissolved in it, we will call it the aqueous layer. And that layer was then mixed with chloroform, and put into a separatory funnel, and we have 2 layers. If we had taken that aqueous layer and mixed it with methanol, ethanol, acetone, we would not have 2 layers, and we couldn't do this extraction. Students sometimes also get confused once they have things in the separatory funnel, they're doing liquid-liquid extraction, about, well, which layer is which? Which layer is the aqueous layer? Which layer is the solvent layer or the organic layer? Well, it depends. Most of the time, the organic layer is going to float on top of the water because most organic solvents are less dense than water. However, some solvents, mostly the ones containing chlorine, like chloroform, dichloromethane, methylene chloride, chlorobutane, those solvents are more dense than water and sit on the bottom. Chloroform is a great solvent for extracting drugs. We have to be careful with it because it is carcinogenic, but we use it a lot, and you can see that's what we're using here, and it's sitting on the bottom. A couple practical tips for SEP funnels. First, when you're mixing things up, you shake them up real nicely like this, and then you invert it like Becky has, and you burp it. You open it up. That's called burping it, because gas builds up in those things, and solvent can cause things to pop off or spray around. Another simple tip that might seem a little bit silly, but is pretty useful to remember, is we see here Becky's having trouble draining the separatory funnel. She's just getting drip, 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 and if this is happening to you and you're getting frustrated, it happens to the best of us. But Becky has, well, she hasn't actually forgotten, but she's demonstrating for us. If you forget to take the top off, then it's not going to drain nicely. So again, make sure that you pull the top off when you're draining a SEP funnel so that it drains nicely. Also, be really conservative when you're draining a SEP funnel. Here you can see that we've made sure to stop the SEP funnel before any of this garbage gets into your sample. If you lose a little bit of the solvent, you see there's a little bit of solvent sitting there, we can try and get that little bit more, but don't. Just leave it. What's more important, it's okay to lose a little bit of that nice transparent solvent, but you don't want any garbage in your sample. It's very important not to pull any garbage into your sample, or you'll have to keep going with the extraction to make it pure.
Pay attention to this part. It's really hard.
Okay, so I put this at the end, but this is a really important part of these extractions. So if you're dealing with compounds that have what we call ionizable groups, if they have acidic or basic properties, then you have to control the pH if you are dealing with water, if you're dealing with an aqueous layer. So really, never use water again when it comes to drugs, because pretty much all drugs are going to be acids or bases. There's a few neutrals. Most drugs are bases, and both tryptamine and methapyroline are bases. Now I've shown the structure of tryptamine here, and we know that tryptamine is a base because of the amine, and I've shown the primary amine. Now what happens is, at high pH, this amine, the structure exists as we typically draw it, and it behaves nicely according to the solubilities that you read about in Swig drug or that you read about in Clark's. So this will go into organic solvent, maybe it'll go into water. Most of the time these don't go into water well, but this is called the free base form. So when you're at high pH, you're in the free base form. However, when you drop to a low pH, if you add acid to it, like we do in that first step with acetic acid, then it's protonated. It's that NH3+, and it is an ion. And that dissolves in aqueous. It's very, very difficult to have ions dissolve into any solvent. So even if you say, oh, tryptamine dissolves really well in chloroform. Well, if it's protonated, if it's in its protonated form or its salt form, it's not going to dissolve well in chloroform. It's only going to dissolve well in water. So you have to be very, very conscious of which form your drug is in, and you switch it back and forth. So when you add the acetic acid to the chocolate in the beginning, it protonates it makes sure all the tryptamine is protonated, and that acetic acid is an aqueous layer. That acetic acid is water. It's almost all water with a little bit of acetic acid in there. And so the tryptamine dissolves in there. Now, if you want to take that acetic acid layer and push the tryptamine out of that layer into an organic solvent, you raise the pH of that aqueous layer until you convert the tryptamine to the free base form, and that will push it into an organic solvent, and then it will be an organic solvent. Then if you want to push it back into an aqueous layer, you could add an aqueous layer that's at low pH and shake it up. That'll convert it back to an ion, and it'll go back to the aqueous layer. And you can go back and forth like this. And that's what we do most of the time when we clean things up, is we push it back and forth between the ion form or the salt form and the unionized or the free base form. We push it back and forth between an aqueous and an organic layer. That's 99% of cleaning things up in drug chemistry.
Ions dissolve in water.